Okay, now let's try this question in a more general setup. What I'm going to show here is like unrestricted model is the same. So unrestricted model has exact identified case Z1I where Z1 is K dimension, right? And dimension of beta is also K. So the moment restrictions and the number of unknowns are the same. And restricted model has additional instrument, right? I will write this as M dimension. So say M is greater than K. So we have extra identification, right? I will write M minus K as Q. Q is the degrees of freedom. And I will show that the first, sorry about that. So unrestricted model will satisfy all the moment conditions. It is pretty straightforward. I'm not going to prove that this is exactly the same as one-dimensional case. There is no difference. It will be simple enough. But also what I'm going to show here is actually n times restricted criterion function is converging to chi-square q. That's what I'm going to show. To do that, what we learned in class was, say, if x follows normal distribution 0 and sigma, it is say k by 1, it's k by k, and then we learned x transpose sigma inverse x follows chi-square k, okay? But now we are going to think about an additional step, right? So first, we are going to write sigma to minus 1 over 2. It is a matrix, like you are taking square of the matrix. So if you think this kind of variable, it will be standard normal distribution in k dimension. So it is k by 1, it is k by k. Okay, or let's simply just think about k dimensional standard normal distribution. And what I'm going to do here is, okay, let's simplify. So y is k dimensional standard normal distribution, and I'm going to show that y transpose p times y will follow chi-square q, where q is the rank of p, if p is idempotent, right? For an idempotent function matrix P, we are going to define distance. For example, it is like this. For example, when y is k dimension, say y1 up to yk, but P is a function that has, say, 1, 0, 0, 0, 0, 0, 0. Everything is 0. Only 1 by 1, 1 comma 1 element is 0. In this case, y transpose py, it's just y1 squared. So it is just one-dimensional chi-square. Or if you have like a little more ones in the diagonal elements, then say if you have 3 ones, then you are going to get this. Then it will follow chi-square 3. So that is what you could think about in this case. Okay, then let me see, where do we have to start? We are going to start from the general instrumental like influence function, right? You remember the influence function looks like this. Okay, so this is the general influence function we learned in class. And then let me think about it. And then now let's think about the sample moment evaluated at the estimator, and it is 1 over n summation large Z, including all instrument here, yi minus xi transpose beta hat. Okay, and then I'm going to rewrite this as zi. Y can be written as xi transpose beta 0 plus ui minus xi transpose beta hat. So it is again zi. Here ui minus xi transpose beta hat are n minus beta 0. Alright, and then what I can do here is it is just expand. You expand the terms minus sample average of zi xi transpose, and here the sample estimation error can be written using influence function. This is your sample moment. Okay, sample moment can be written this way, and then furthermore, by the way, right, let's try this. By the way, this is g hat. Okay, I'm going to write it as g hat. So sample average of ziui minus g hat times this guy equals, plug in the influence function g transpose omega inverse g inverse g transpose omega inverse, and here gi like so this part equals ziui, if you remember what we did in the earlier case. So that means we can factor out these guys together. And I will just assume that gi hat, because gi hat converges to gn hat converges to g, right? So it is sample average converging to the true mean. So I'm going to just write this as g for simplicity. And then that becomes 1 over n, excuse me, identity minus g times g transpose omega inverse g inverse g transpose omega inverse times 1 over n sample average of zi ui. This is what we get for the sample average, right? I'm just rewriting this in this form. Okay, now then we will think about the criterion function. Criterion function looks like sample average transpose, like instead of weighting function I'm going to just write omega inverse, right? The limit will be omega inverse gr hat beta hat rn. So this is the criterion function, and then we have using the previous notation ziui transpose and I minus g transpose omega inverse g inverse g transpose omega inverse transpose omega inverse, and I minus g same thing. So all this same thing comes here times sample average of ziui. That is what we get here. And then if you rewrite this, if you think about it, we have say 1 over n. We can write this as excuse me, I will write this as omega to minus 1 over 2 times ziui transpose p times 1 over n summation and omega to 1 over 2 minus 1 over 2 times ziui, where p is I times I minus omega to minus 1 over 2 g times g transpose omega inverse g inverse G transpose omega to minus 1 over 2, right? So it is annoying, but if you do it carefully, you'll find this equality easily. And then also it is easy to see that P is symmetric. And also you can also see that P is idempotent, right? Because it is a like residual matrix, right? This is the projection matrix form. So this is a residual matrix. Now what you have to do here is you have to find the rank of P. Rank of P is like this is M by M matrix. So rank of P will become M minus rank of uh, this matrix. This matrix will come here, right? The matrix comes here, but this is easy to calculate because omega is full rank, so it does not affect the rank. And by the full rank assumption of the identification assumption, the rank of G is K. So this rank, the rank of this guy is determined by this rank, right? So like, let me put it this way. This is full rank, this is full rank, this is full rank. So they do not affect the rank. So the rank is determined by those guys, right? So as a result, the rank of P is M minus K, which was Q, the degrees of freedom we defined earlier. And then this is exactly the case we learned here. It is the general, like here, the general definition of chi-square Q distribution. Of course, one more thing you have to show here is this is standard normal distribution because you are standardizing the variance of Zi Ui is omega. So you are standardizing the variable using the square root of inverse of the square root of the variance. Okay, this is the general proof which requires some additional linear algebra. I hope it helps.